Okay, so welcome back, everybody. So now it's my pleasure to introduce Huang, who is actually with us in a group of mathematical physics. So maybe you, and he will talk today about second-order differential geometry and stochastic geometric mechanics. So you can just pin this on your t-shirt.
Okay. Sure. Okay. I just so thank you. Thank you. I would like to thank you for the organizers, Annabella, Jean-Claude, and Leo for the preparation for this nice conference. And I also want to, apologize. Oh, I'm sorry. So I also need to apologize in advance for my for my bad English speaking. Please keep some patience to me. So, okay, today I'm going to talk about a recent project with joined with Annabella and Jean-Claude. Basically we establish a new framework to a stochastic version of geometric mechanics, actually. And I was planning to name our framework. Okay, I was just planning to name our framework by stochastic mechanics, but Jean-Claude said no, because stochastic mechanics has already been used by Nielsen, right? So then I would like to use the stochastic geometric mechanics, because the framework is actually based on geometry. So I think the core is still geometric mechanics. Okay. So this is the contents. It looks quite long, right? Don't be scared. Okay. So in the first part, I will introduce of our motivation and our methods, and then I will introduce to you what is second-order differential geometry, and what we have obtained from the old results to some new results. Okay, and the third part is stochastic symmetries, and the last part is stochastic mechanics. Is about the stochastic Hamiltonian and the stochastic Lagrangian and HJB equation, Hamilton-Jacobi-Bellman equations. Okay, so this is so let's see what's our motivation. So basically, in the classical theory, we have the whole picture, which is we have two parts. The first part is the calculus of variation, or the analytical parts, and the second part is the geometric mechanics, and it's basically is a geometry part. So those two parts can be connected by the Hamilton-Jacobi equations, right? And from Hamiltonian-Jacobi equation, we can reach to the optimal transport theory and to the optimal control theory. Basically, by the from the framework of calculus of variations, and we can also have the Lagrangian mechanics and the Hamiltonian mechanics by the geometric structures, like the symplectic structures and contact structures and so on. So that's the classical picture, and it's already well developed, right? we know that we have lots of mathematicians like Arnold, Marston, and like Lyons, Villani, and so on. So that's already well developed. So let's look at the stochastic picture of. So we also have two parts. The first part is a stochastic calculus of variations, and the second part, what we is what we call the stochastic geometric mechanics. So the first part, okay, the two parts also be connected by the HJB equations, Hamiltonian-Jacobi-Bellman equations, right? And from the HJB equation, we can reach the stochastic optimal transport theory and the stochastic optimal control theory and Jean-Claude Euclidean quantum mechanics theory, or he also called that the stochastic deformation. And okay, so this part, the part of stochastic calculus of variations, is also, is also quite well developed, because we have lots of results in this part, like you have already seen from Mikami's talk. Mikami and like Leonard, the Christian Leonard, right? And they have lots of results in the stochastic optimal transport theory, and Jean-Claude and Mikami, they also have lots of results in the stochastic optimal control theory, and Jean-Claude himself developed a theory of Euclidean quantum mechanics, and he has lots of contributions to his theory. And actually, this theory, the Euclidean quantum mechanics theory, inspired us a lot for our new theory of stochastic geometric mechanics. So in the part of stochastic mechanics, geometrics mechanics, like the stochastic Hamiltonian or stochastic Lagrangian, or their connection, like stochastic version of the Lagrangian transformation, there is almost nothing, right? And no results, almost no results in this aspect, because this aspect need some some geometric structure, actually the stochastic version of geometric structure. So that's what that's what we did in this project. Okay, that's a motivation, and okay, I will also say something about our methods. Basically, we need to establish the stochastic geometric mechanics. It's actually a interdiscipline of like stochastics and geometry, right? It's an interdiscipline of stochastics with geometry. By the way, it's not the probability theory with geometry. It's just the stochastics with geometry. Okay, so in the history, there actually are two approaches to do the interdiscipline of stochastics with geometry. The first is called the geometric stochastic analysis, or called stochastic analysis of manifolds. This theory is mainly focused on the Stratonovich type SDEs on some classical differential structures like on the Riemannian manifold or on orthogonal frame bundles or Lie groups or so on. And this approach is also very well, widely studied by originally by Ito, Ito's formula, by Ito, the Japanese mathematician Ito, and then by Malia Wang, and by Bismuth, Elworthy, Stuk, Huang, and Annabella, and some Chinese mathematicians, Fang Shizhan, and Li Xuemei, and Xu Pei, and so on. And in this approach, because they use the Stratonovich type SDE, so basically the Leibniz rule still remains. Okay, so they have lots of stochastic version of operators like the Lie derivative, the Lie derivative here, and the covariant derivative here, and the horizontal lift, and the curvature tensor, and so on. And they just replace the vector field by a Stratonovich type stochastic differential. So basically, in this approach, the stochastic differential here in the subscripts, the stochastic differential plays a role of vectors rather instead of covector. I think that's an abuse of notations, because they use the differential notation, but it does play a role of vector instead of covector. So in this way, all the Leibniz rule remains. So all the geometric every calculus in the geometry just can be parallelized to the stochastic case. So that's the first approach, and the second approach is called the stochastic differential geometry, or second order differential geometry. So basically, the stochastic and the second order are always coupled with each other, because basically that's a corollary of Ito's formula, right? Because in Ito's formula, the everything is second order. So the stochastics is always coupled with second order, or we can say they are equivalent in some sense. Okay, so in this approach, they just incorporate the rule of the Ito's formula into the differential structures. So basically, they change the differential structures themselves. Okay, they don't use the stochastic. They don't use the classical differential structure like the Riemannian structure or bundle structure or the groups. They change the differential structures. They build actually some stochastic versions of differential structures. So, and this approach is originally developed by Schwartz, actually, and then by Meyer and Emery. So, but actually, I don't know why this approach was not paid much attention to, by both either by probabilist or by geometrist. I don't know why, but that's a fact. Okay, so for this reason, they have very less results because they don't have they are not be paid much attention to. So they have very less results. They only have like some results like the second order vector, or they define the second order vector and the second order covector, and they define the so-called ethos bundle, and they establish a so-called Schwartz principle, and nothing more. That's all of their results actually. So in this project, we will continue the framework of second order differential geometry, and we will develop more, and we will use this framework to do geometric mechanics. So that's why we call that the stochastic geometric mechanics, right? Okay, so now let's let me introduce to you what is the second order differential geometry or stochastic differential geometry. Okay. So in the classical differential geometry, they always start with, you know, every textbook about classical differential geometry is always starting with tangent vectors, tangent fields, and they are actually the tangent vector fields are actually the generators of one parameter flows, right? Of diffeomorphisms. And in second order differential geometry, the starting point is the second order differential operators instead of vector fields, because vector fields are actually first order differential operators on manifold, right? So the second order differential geometry start with second order differential operators, and by Ito's formula, we know second order differential geometry is are just generators of Ito's diffusion, right? They are just generators of diffusions. So you know, you see second order and the stochastic are coupled, right? And there is a second order, a typical second order differential operator A looks like this, and we have the change of coordinates formula like this. So by the change of coordinates formula, we can define a bundle, right? Because, you know, just like the classical differential geometry, every bundle is defined by a structure group, right? And that structure group is determined by the change of coordinates formula. So as soon as we have the change of coordinates formula, we can define a bundle, which we call the second order tangent bundle. And the structure group is actually already defined by Schwartz. And they call the ethos bundle, they call the ethos group. That's the structure group. And this, and the structure group acts on the left to the fibers, to the typical fiber by this formula. And you can see this action formula is actually implied by the change of coordinates formula, right? Okay, so then we have the second order tangent bundle. Actually it's a nonlinear bundle over n, and its typical fiber is a space RD times the second order symmetric tensor over RD. And the structure group is just the Ito group. And you can see the typical fiber is still a linear space, right? The typical fiber is a linear space, but the structure group is not a linear group. So it's basically not a linear bundle. And we have the local frame for that bundle is just a base, a natural base, right? The first order operator, the second order operators, and they just form a local frame. And a typical second order vector looks like this, and you can see that the coefficients of the first order parts, the AI, is not a vector. Actually, it's not a vector. This is a fact from the change of coordinates. You see, the change of coordinates is not a tensor type, right? So basically, AI is not a vector, but the coefficients of the second order part is a tensor. Is a tensor. That's also a result from the change of coordinates formula, and it's actually a symmetric 2-0 tensor, and we have we have a relations. We have a relation between the second order tangent bundle and the classical tangent bundle by this short exact sequence. Okay, every map is canonical actually from the definitions. And what we need to say is that this short exact sequence is actually split when we specify a linear connection on M. You will see that later. And this is very important when we establish when we define the second order Legendre transform. Actually, the split property is very important when we define the second order Legendre transform. Okay. And we of course we have the dual object, the second order cotangent bundle, which is the dual of the second order tangent bundle, right? And it's a dual, and typical fiber is a dual, and the structure group is still Ito group, but the action is from the right. So that's a dual action. And we also have the coframe. The coframe, that's a notation from originally from Schwartz and from Meyer. So that's a coframe. The d square xi and the dxj dot dxi. That's their notation. They use this notation to denote the coframe that dual to the frame of the to the canonical frame of the second order tangent bundle. Okay, and we have a typical second order covector looks like this, and dual to the second order tangent case. We know that the coefficients of the second of the first order parts of this covector, the coefficients of the first order part is a covector, but the second order part is not a tensor. That's a dual result to the tangent case, right? It basically is also a corollary of the change of coordinates formula. So. Okay, so and we introduce canonical coordinates on the second order cotangent bundle, which we denote as XPO. because you see x is just xp. If you are familiar with symplectic geometry, xp is just the canonical coordinates for the classical cotangent bundle, and the extra coordinates is designed for the second order case. Okay. And we also have the short exact sequence, which is just the dual short exact sequence to the tangent case. And that's the relations between second order cotangent bundle and the classical cotangent bundle. Okay. And you can see that this dot map here from the symmetric tensor bundle to the second order tangent bundle. So the dot map here, the large dot, it's just the little dot here. They are the same. Okay. And this short exact sequence is also split when we specify a linear connection. You will see later. Okay. And okay, now we have the Ito type SDEs on manifolds, which is this type, and the coefficients B and sigma transposed with sigma, sigma composed with sigma transpose. Okay, this object is a time-dependent second-order vector field. So basically, according to the definition of second-order tangent bundle, this B is not a vector. You see, this B is not a vector. But the sigma composed with sigma transpose is a tensor. Okay. So that's why I use this kind of B, not the usual B. Okay. Because it's not a vector. And we have some notions that borrowed from Nielsen's theory. The basic notion is just the Nielsen's derivatives, and we need their version on manifolds. So we just define Nielsen's derivative on manifolds, which is we denote for a diffusion valued on a manifold, we denote capital D of X and capital Q of X as the generator of X. So basically, if we denote the generator of X by B and A, then D of X is just B and the Q of X is A. So Q of X is a tensor, but the D of X is not a vector. So remember this fact. And in local coordinates, they have the very nice formula. It's just a limit of an expectation of limits. So and as I have mentioned, D of X is not a vector. So in order to define a vector type Nielsen's derivative, we need to specify a connection. Actually, we need another structure of a linear connection. And if we have a connection, then we have the normal coordinates, and we can use these normal coordinates to define a vector. So, and this vector type Nielsen's derivative I denote by D of nabla of X. So that's a vector, right? That's different from D of X. And the relation of the vector type derivative with Nielsen's derivatives is given by this formula as soon as we have a connection. And now I will introduce to you more developments on the second order differential calculus. That is, I will show you how to do differential calculus of second order, okay? So in the classical differential geometry, the tangent, actually, if you remember, then in the classical differential geometry, we have lots of equivalent definitions for the tangent vectors, right? At least, if I remember that correctly, at least we have 4 different equivalent definitions for tangent vector, and one of the definition is by the equivalent class of smooth curves, right? So two curves, gamma and gamma tilde, is said to be equivalent at the base point Q if they have the same value at Q, and if they both start at Q and they have the same derivative at Q, actually. So then we have this type of diffeomorphism. The tangent bundle can be diffeomorphic to the equivalent class of those smooth curves, right? And then the canonical coordinates on the tangent bundle is just defined by the denoted by x and x dot, and x dot is defined by the derivative of the curves in the equivalent class. And in second order case, we just do the similar things, right? You can see we just replace the smooth curves by diffusions, and we replace the classical derivative here, the classical time derivative by Nielsen's derivative, you see. And we can similarly define a equivalence relation between diffusions, and we can also have a equivalent description for the second order tangent bundle. It's just by the equivalent class of diffusions. And the equivalent class we denote by JQ of X, okay? X is a diffusion start at Q. I use this notation I of M to denote the diffusions of M, okay? And then we also have the canonical coordinates on the second order tangent bundle, which I denote by X, dx, and QX. So basically, X just maps the equivalent class to the base point, to the coordinates of base point, and the d of X maps the equivalent class to the Nielsen's derivative and Q, and also the quadratic Nielsen's derivative, actually. So that's the canonical coordinates on the second order tangent bundle. And also similarly to the classical differential geometry, okay? In the classical case, we have the push forward and the pull back mapped by smooth curves, which is just you see gamma push forward the time direction to gamma's tangent direction, right? And so that's classical. And similarly, we can define the push forward and the pull back by diffusions very similarly. So that's generalization from the classical differential geometry, and we have more, like the second order push forward and the second order pull back by smooth maps, and we have Lie derivatives of a second order tangent fields with respect to a classical vector field V. And the lead derivative of a second order cotangent field alpha with respect to the classical vector field V. So that's very similar to the classical case. So I just put the name over here. And okay, now we reach the part of stochastic symmetries. Actually, it's also very similar to the classical theory, because in the classical differential geometry, the symmetries of ODEs or PDEs are always related to the jet structure, the jet bundle, right? So we need to, in order to do this similar to SDE, that is, in order to do symmetries for SDE, we need to define the stochastic version of jets, which we call stochastic jets. So that's basically also defined by equivalent relations, and that's basically that's from the point of view of the definition of the tangent bundle, tangent vector by the equivalent class of smooth curves. The idea is the same. So, and we denote the stochastic jet space by JSM, and this space is only a topological space. We cannot handle a differential structure on it. Actually, I don't know how to handle a differential structure on such space, because it involves the randomness, right? Involves the little omega, the sample, right? So, but if we fix a little omega, then this space is one-to-one corresponds to this trivial bundle, the R times TSM. Okay, if we fix an omega, then they are one-to-one correspond. So, and so if we fix an omega, then we can handle this space differential structure, right? By this one-to-one correspondence, right? Okay, and on the other hand, the second order cotangent bundle can also be defined by germs, just like the classical case. You know, in the classical theory, the cotangent bundle can be defined by germs. So in the second order case, we can also do the same thing, but we just replace every first order derivative by second order derivative. And in this case, the second order tangent bundle times R is diffeomorphic to the classical second order jet bundle. You know, that's a very interesting structure, because you see the R times TSM is basically is dual to TSM times R, right? There are dual objects in the jet bundle sense. So basically, we can say that the stochastic jet bundle is dual to the second order jet bundle. So that's also, you can see that the stochastic is coupled with second order. So you can see everywhere in this talk that stochastic is always coupled with second order. So okay, and now we have an intrinsic definition for stochastic differential equation for SDE. Okay, that's also very similar to the classical case, because in the classical case, an ODE or a PDE can be defined as a submanifold of a jet bundle, right? So in the second order case, we can do the similar thing. We can define an SDE as a closed embedded submanifold of the model jet of the stochastic jet bundle R times TSM. Okay, so that's a very intrinsic definition for SDE. And we can, the solution of this SDE is just a triplet. First of all, we need a filtered probability space. That's a usual setting, right? And we need an adapt process, and so such that the SDE is fulfilled by this process X. So that's what we mean. The X is the process X fulfills the stochastic differential equation. That is the jet of X belongs. The jet of X belongs to S. Belongs to the submanifold. Then we say X satisfies the SDE as okay. And this definition is not very intuitive, right? So I'll give you an example. Basically, if you give this submanifold a local defining function, then the condition that Jt of X belongs to the submanifold S is just you see equivalent to the vanishing of the local defining function, right? So then we actually have an equation. So in the as soon as we have a local defining function, then we can have an equation. That equation is just an SDE. Time. Okay, I will be quick. Okay, so a typical example is that if we choose a local defining function to this type, then we go back to the ethos SDE. Okay, then we have more parallel definitions like prolongations, push forwards, and prolongation of bundle morphisms, and so on. Then we have and also we have the definition for symmetries of SDEs, and infinitesimal symmetries of SDE. Basically, the symmetries of SDE is a bundle morphism that transform a solution of the SDEs to another solution of S. So that's a symmetry. Okay, then we have the prolongation formula, and we have the determining equation for symmetries for the ethos SDE, and we also have the. Well, I don't have much time, so I will be quick. We also have the mixed contact structure on the stochastic jet bundle R times TSM, and you see there is a terminology mixed, right? Basically, mixed means it's first order in time, but it's second order in space. You see, the contact form is looks like this. It's basically second order in space and the first order in time. So that's why we call it mixed. And we have the symmetries for the contact structure or the Cartan structure actually. And then okay, as you can see, The symmetry theory is based on the contact structure on the second order tangent bundle, but the stochastic mechanics is actually based on the contact structure on the second order cotangent bundle. So that's okay. Then on the second order cotangent bundle, we can also define the tautological form and the symplectic form and the Hamilton vector field. And we can have a stochastic version of Hamilton's equation. Looks like this. Is actually an equation formulated by Nielsen's derivative, right? And if now for this equation, we can actually solve it by let the process X to be horizontal, which means it's random horizontally. That is, it's composed of determined second order form with a random process. Okay. Then we can solve that Hamilton's second order Hamilton's equation, and okay. And we also have the mixed contact structure, and by this by defining a mixed Poincare-Cartan form, right? It's mixed because it's first order in space and it's first order in time, but second order in space. Okay. And by this contact structure, we can derive the second order version of Hamilton's principle. We can derive the Hamilton-Jacobi-Bellman equation actually by the canonical transform of the second order contact structure. And more general, we have a generalized Hamiltonian-Jacobi-Bellman equation. Okay. And as an example, we have the Brownian flow on Riemannian manifolds. And by this example, actually, you can see that the Brownian flow on Riemannian manifolds is just the stochastic analogy of the geodesic flow on Riemannian manifolds. And okay, now we in order, as I said, in order to define the second order Legendre transform, we need to specify a connection, because if we specify a connection, you see, then the connection can induce a canonical projection from the second order tangent bundle to the classical tangent bundle. Okay, and in the cotangent case is also similar. So by this canonical projection and injection, we can have the Legendre second order Legendre transform, and the inverse of that. Actually, this second order Legendre transform is not invertible, but we can have a canonical way to define the inverse of it. Okay, and we can also as soon as we formulate a stochastic variation, no problem, we can have the stochastic Hamilton's principle, which is this form. You see, we have the stochastic Euler-Lagrange equation. Looks like this, and the capital D is a stochastic version of the covariant derivative, actually. And we can go from a stochastic Euler-Lagrange equation to the Hamilton-Jacobi-Bellman equation in this typical case. And by the way, there is we have some relations with Schrödinger's problem by optimal transport. Actually, that's a requirement from Jean-Claude, because that's a topic of this conference. So I need to make some relations. But we do have some relations, right? And in the stochastic Lagrangian formulation, we have a reference tensor, which is a symmetric 2-0 tensor. And this tensor actually plays the same role with a reference measure in the Schrödinger's problem. And if the reference measure equal to the law of the reversible Brownian motion, then the reference tensor is just the Riemannian tensor. Okay, and the relative entropy is just is just our action functional. They are just the same. Okay. The last thing is we can transform from the second order Hamilton's principal function to action functionals. Okay. Actually, in the stochastic case, the action functional is the expectation of the Hamilton's principal function. You see. So that's all. And thank you for your attention, and thank you for your patience. Okay.
Thank you, Xiao. So as usual, does anyone in the room or online have any question? People's clapping, by the way, in the chat. Anyone in the room? I have one, because I'm not a geometer, I'm not a stochastic analyst as well, but pretty much in the same spirit as Max's question is, so can you put back the previous slide? Just the previous one, when you talk about the connection with yeah, exactly this one. So how much does that help me as a guy working in Schrödinger and optimal transport? How much this kind of new geometric framework helped me and tell me that I didn't know already somehow?
Okay, as I said, you see the connection to the Schrödinger's problem is just we need to first of all we need to formulate Schrödinger's problem on manifolds, and in the classical Schrödinger's problem by optimal transport, I'm not sure, but they're always formulated on the Euclidean space, and they have the Hamilton-Jacobi-Bellman equation on the Euclidean space. But if you do the same thing on the manifolds, then you can see you specify a reference measure is equivalent to specify a reference tensor, actually. Reference 2-0 tensor, and if that reference measure is just the law of Brownian motion, then the reference tensor is just the Riemannian metric. So that's I'm sorry. So and you see, and I think that's the case. Oh, I'm sorry. Yes, I don't know if there is anyone to do Schrödinger's problem on general manifolds. I'm not sure.
In some terms, the optimal control gives you a Lagrangian transport. But still, there is an Hamiltonian framework associated with the
Yes. you are right. The connection is just there are connections from Schrödinger's problem with Lagrangian mechanics, but instead of the Hamiltonian's mechanics. Right? Yes.
So do you want to have a framework which is more general with respect to the reference process that you would choose? Is that the direction? Yes.
Yes, actually, yes, that.
Sorry. Yes, that's actually what I'm thinking in last few days. That yes, I think I can generalize to a more general reference measure with a drift actually, because in our case we only have a diffusion term. We don't have a drift. But I'm still thinking about that. I think it's a trivial generalization, but I still need some check. Yes, thank you.
In a way, the mechanics is a bit more.
Yes, I think I think the only thing we need to revise is to add covariant derivative with that drift in the Euler-Lagrangian equation. Okay, but I need some check.
Okay, then it's the end of the morning session.
Yeah, thank you all. And for everyone online, we will resume at 2 p.m. Lisbon time, so 3 p.m. for the rest of Europe. And thank you, everyone. Ouais, on laisse Yann tout seul. Ouais. Moi, je fais pour.